It's my great pleasure to interact with the researchers and esteemed faculty of Indian Institute of Technology, Delhi. I will share a brief presentation on the topic. I hope you all can see the screen or PowerPoint. Can one of you confirm, please?
Yes, sir, we can see it.
Okay, thank you. So today we are going to talk about role of nanotechnology to meet United Nations Sustainable Development Goal and their current status and future perspective. And I will take an example specific to agriculture and how that is important and what is their role to meet the different sustainable development goals. So at the very beginning, the question comes that why we are actually discussing UN Sustainable Development Goal, because our country, India, is a signatory for the United Nations, and we are the member of United Nations. So we are the signatory to meet the Sustainable Development Goals, which are identified for the betterment of humanity and the surroundings of us. So when we talk about sustainability or sustainable, then we talk about that the resources that we are having, the resources we are accessing today, can we keep them in the same manner for the future generations? And those resources to fulfill the need of today, but also to keep them accessible for the future generations. So the United Nations have identified about 17 sustainable development goals, which we all have might have seen at some sort of time whenever we have seen the news articles or some other platforms, which starts with the poverty and ends with the collaboration or partnership for various goals. Particularly all these, if we look on that, whether it is hunger or poverty or health or the water or some related to the environment, whether it is climate or water in life, water in land, most of them are related to the agriculture or the basis on the agriculture. How? That when we have the enough food or quality nutrition, then they can meet the zero hunger address, they can provide the good health and well-beings, they can help the climate related issues, whether it is on water, on land, or in the air as well. So the question comes that what is the need and to achieve them now? Because of the some reasons, whether it is like deforestation, whether it is waste disposal or air pollution, global warming, these are some of the points I have mentioned here, which basically because of the human actions, human activity, majority of these points are affecting the human lives in one way or another way. And since the Center for Rural Development and Technology, CRDT, also involved with various research and development related to these points, that how to address these points. So these are the points basically, whether it is related to the forest or whether it is related to biodiversity or water or the other pollution caused by the human, is also linked with some fundamental challenges, which may be like education and skill training. I use the word here, the skill training, more than the education here, because the reason is when the people know that how it is going to affect me, but how it is going to affect the generations. For example, if we are going on the road, we have taken the banana chips, we have eaten the chips, and then we have thrown the plastic package on the road or roadside. So because if we feel that it is not going to affect me, but if we educate the people enough that how it is going to affect the generations, not today but in futures. So if there is enough education or skill training, these challenges can be minimized. Similarly, there are gender and cultural inequalities when we talk about across the world. And then there is a distribution of the natural resources. For example, distribution of the natural resources, I meant here that we have some place we have more water, whereas and in that particular area, the water requirement is less for agriculture, for example. Whereas some other part where there is an adequate land to do the agriculture, but there is a lot of salinity or there is no water. So the distribution of natural resources, this is just an example of water, but there are other critical examples maybe related to like fertilizer, for example, which is like more of the organization I belong to or my expertise are. The ongoing situation in some other part of the world, which is also already affecting the prices of the natural gases, which basically act as a raw material for producing various agrochemicals, particularly fertilizers, or the deposits, natural deposits like rock phosphates, which basically the raw material for phosphate-based fertilizers. And you can see how they are affecting the prices of diammonium phosphate, which is a raw material for DAP, which is one kind of fertilizer. So and other resources as well, whether it is the gas or resources like which is required for health or other infrastructures. So these are like different distribution. These are the major challenges causing the problem. If we further go deeper, the basic need of the human is related to food, water, and health. This is very primary requirement for human to survive, and for that, if we have an adequate agriculture or enough agriculture perspective, we can address these problems, whether it is related to the food security or the health security in terms of providing the nutritious food. And then if we have a sustainable or precision agriculture practices, we can save our water from getting polluted, whether it is from nutrient runoff or emitting various harmful greenhouse gases from the different fertigation techniques. So we can secure these three major challenges, which are also part of the UN Sustainable Development Goals. Then there is a discussion came once the Japanese government brought down their one of the agenda that is called Society 5.0. In that, they are discussing that the Society 1, where we were talking about like hunting and gathering and eating and just surviving, and the Society 2, where we are talking about modernization of agriculture, then moving to third, where the industrial development, industrial advancement, and then Society 4, where we integrated with the information technology, bioinformatics, and then ultimately we move to now the Society 5.0, where is an integration of both the physical world as well as cyber world, and the role of data science, role of artificial intelligence, role of integration of supercomputers to monitor the progresses of various economic developments or the human developments or the environment related developments, or even the negative consequences, also to monitor them in the real time and then making the policy and taking the decision to solve those problems. So these are the different concepts are coming in to ultimately the aim of whether it is Society 5.0 or Sustainable Development Goals. They all are the goal is the common, which is the betterment of the humanity for today and for the future generations. And nanotechnology is at the core of most of the technologies being developed today, or the technological solutions being developed today, whether they are belongs to the sensor to detect or predict the problems or predict the health or situations, or whether they are related to energy security, whether they are related to the medicine or health, or whether they are related to the data science or artificial intelligence or environment or towards machine learning and so on. And all these are going to translate for our waste management, whatever the waste we are generating, because we are an open system, open ecosystem. So in open ecosystem, we are also losing certain things, and we are not 100% doing everything recycled. So there are generation of the waste and energy. So how to conserve them or how to restore them, or related to the developing the system which are more like energy efficient, water efficient, or input ingredient efficient, or turning several things into like circular economy, so that we can use and we can reuse, and during reuse and reuse we can generate certain source of an income or an employment, or transport which is like less emitting carbon dioxide, or utilizing more like renewable energy resources, or related to biodiversity. And the loss of biodiversity is also because of the climate change, and climate change is because of the lot of greenhouse gases emission and other factors. So what I want to say here, that overall all the factors mentioned here are interdependent, interlinked to each other, so that all the parameters can solve or have some potential role of nanotechnology because of its properties. When we create any material, engineered material at 1 to 100 nanometer, because if we see nanomaterial in our environment, we have a lot of natural nanomaterials as well. For example, the soot particles, the pollution, they are also some part of that is also in nanoparticle size range. Similarly, a lot of other things surrounding to us these days, like virus, like even this coronavirus, which is also in nanometer size range, like 1 to 100 nanometer size range. Similarly, there are several subcellular organelles in our body, in our cells or plant cells. They are also in nanometer. But what we are talking here is an engineered material which is tuned to synthesize by controlling their properties between the size range of 1 and 100 nanometer, at least at one dimension. So these engineered nanomaterials having very high surface area to volume size ratio, they are having quantum phenomenon, quantum properties at the nano scale, which shows the better bio interactions. And when we talk about these nanomaterials, they are offers, and if we see some in the past decade, we can see that nanomaterial help in advancing or providing disruptive game-changing breakthroughs or innovations rather than an incremental improvements. And this is mainly because of its properties, whether it is quantum effects or surface area to volume size ratio, or improving the interfaces interactions. So how this nanotechnology can help us to take or help us to meet the Society 5.0 goals or the UN Sustainable Development Goals. For example, I'm laying down like few examples, and then I will focus on agriculture part. Like for example, if we take the example of health and medical care, nanomaterials can provide us an opportunity to develop the system, to develop the equipments which can help to do the preventive checks or the robotic care. So what this will provide, that this will help us to extend the healthy life and reduce the social cost with the precision in terms of like checking the health, monitoring the health in real time. These days, we all are having smart watches or smart bands, which can check our health in real time, how much calorie we have burned, how long we have walked, and then what is the sugar level in our blood, or what is the oxygen level in our blood. So everything we can monitor, and these all are some sort of based on chip technology, and where we are using graphene semiconductors and like that. Similarly, related to energy supply, whether it is perovskite based solar cells or the several equipments which are being developed to generate the energy on site where the consumption is required. So today we are using the energy which is producing at somewhere else, and it is being transported or through various grids and providing to our home sites. But we know that like these days we are also translating towards the solar energy which we are generating on our roof and consuming at our site. So that is reducing the help in reducing the greenhouse gas emissions or stable energy supply. As recently the matter also discussed at the initial of this talk by the madam, that there is an energy problem. And this is very common, not only in India, but across the world, in many parts of the world. Then the food and agriculture, nanotechnology can help providing more like an automatic resources, whether it is fruit seed sowing or the crop care or the crop harvesting or crop nutrition, and then the optimal delivery. These days, or IIT Delhi also demonstrated on this last Republic Day about the drone technology. So there are like drones to do some light show, but these days IFCO is also involved in advancing drone application for agricultural application or agrochemical applications. So what we are doing, that using the drone, we can also monitor the crop health. For example, drone is fitted with certain camera which can monitor the leaf greenness from the top, and based on that we can determine that what is the nutritional quality or nitrogen percentage in the leaf, and based on that the drone can deliver the nitrogen nutrient from the top, like that. And this is not only the one example, nitrogen, but there are several other agrochemical spray that we are doing on the crop. So it can help in enhancing the crop production, or better farm management, or reducing the food losses or nutritional quality, like that. Similarly, like smart industries, similar like the term we are using a lot related to smart cities. So this can help us to provide the optimal supply chains or automatic fabrications. These days we can see that the 3D printers are being used to develop the buildings, particularly for army, the movable buildings and like that. And this can also help to resolve the shortage of labor, increase the productivity, accuracy and efficiency. You might have questions related to employment, but as we know that there are some sudden requirement, like in 2021, where we have faced a lot of labor shortage problems during the COVID, where the labor movement was happened suddenly, and several industries who were highly dependent on daily wages labor. In that cases, those industries who were like having an option to go on automatic mode, they suffered less compared to those who are highly dependent on the labor. So in such cases, in these nanotechnology based applications or improved equipments can help to have the accuracy and efficiency. Our research group is focusing on nanomaterial synthesis and their application and implications. We are synthesizing several nanomaterials in individual form or they're in their composite form. And we are looking their applications in agricultural applications, whether it is crop protection or crop nutrition, or help crop to avoid the stress, whether it is abiotic or biotic stress. Then we are also looking applications in environment, that how these nanomaterials doing biointerface or eco-interface, where when these nanomaterials released to the environment, how they are helpful or when they are not helpful. So we are looking both the perspectives. Then we are also exploring various nanoscale materials for its pharmaceutical applications, or detecting the disease or diagnosing the disease. We have developed some material like calcium carbonate for cancer therapy, similarly for silica oxide for delivering the drug, target delivery of the drug, similarly some inhalation technology that deliver the drug through just by inhalation to the brain. The same way we smell some smell through the nose, so same way can we deliver the drug to the brain. A detail of our lab was also highlighted in one of the Forbes articles, which I have mentioned here, which basically summarizes the work we have done related to the cancer to crops, that how nanotechnology can help in interdisciplinary applications. I will focus for this talk now, or the remaining part, on agricultural applications that we have done in particularly agriculture. And I'm focusing agriculture because at the early on I have mentioned that agriculture can help addressing most of the UN Sustainable Development Goals, or it is based on that directly or indirectly, because we are directly or indirectly depends on for our livelihood, we are depends on the agriculture, whether it is food or health, or the pollution as well. And I will show some example of that. Nanotechnology is being explored for various applications in agriculture, whether it is to detect the plant health or the plant nutrition status, like using the nano sensors, or nano pesticides to protect the crop from harmful pathogens, or use nanomaterials in genetic engineering to deliver the targeted gene to the crop. You might have read that earlier we were using gene gun, and we were using gold particles to attach the targeted gene, and then using the gene gun we were delivering the targeted gene to the plant cells. But now we have an opportunity where we can actually use gold nanoparticles and just coat the gold nano or gold nano cages in which we can load the desired gene, and just through the simple foliar spray we can deliver that particular gene to the plant cells. Similarly, for the seed coatings to increase the seed germination rate, or to help the early stage seedlings to protect from various pathogens in the soil, or help increasing the activity of soil microbial populations, or soil conditioning against the pH or acidity or several other parameters in the soil. Similarly, there are nano fertilizers which can given both through the soil or through foliar applications. Some for the targeted applications, for example, if we want to increase the size of beetroot, or if we want to increase the nutritional quality of the carrot, then we have to focus the nutrition in the soil. Or if we have to increase the biomass in case of lettuce or spinach, or if we want to increase the fruit quality of tomato, which is also in this diagram, and then we have to focus on like foliar applications, or providing the more nutritious part in the foliage above ground tissues, so using that foliar applications. So our team is working on various parameters. You might wonder that why we are working on this nano fertilizers or nanotechnology based applications. I would like to mention one of the data which is recently published in Nature Nanotech about 4 major crops like maize, rice, wheat, and soybean. And this graph shows that since we started doing active agriculture or intense agriculture since like 1960 and so on, and the global population is rising along with that. So to meet the global demand or global food demand, we have to increase the yield by 2.4% every year to double the production of these major crops in 2050, without bringing the additional land resources under cultivation, if we take the base year of 2008. So here are few points that we have to increase the yield on an average 2.4% every year, and we don't have any additional land to cultivate. In fact, our land is going to decrease, because as you can see that most of the farm field which were around our city, now they have converted into the townships, buildings, roads, bridges, because we need our shopping centers. Because when the human population grow, it not only requires food, but it requires a lot of other associated infrastructures as well. And that infrastructure, to develop that infrastructure, we have to convert either the forest land into the infrastructure, or we have to convert the agriculture land into that. And I have selected for these 4 crops in this, because these are the 4 crops which is grown and consumed in across the world. Across the world, these crops are consumed. So these are the reason to mention these statements. And what are the current problems or foundation of these problems that we are facing here? That if we start with if I would like to mention with the realization of the Malthus theory, and Malthus theory talks that the growth of the population is more exponential, whereas the generation of the resources is the linear, particularly related to the food. So very soon, if we are having at the same rate of production, or if we have the same rate of arable land reduction, or same rate of population increase, then very soon we will reach at the multi-strap, where we will have food insecurity for more people. And you all might have read that more than 800 million people across the world do not have adequate food for on their plate even today. We are already very near to that multi-strap, and we need to solve those problems so that we can really increase in a J-shaped curve to our crop productivity with crop nutritional quality. But there are some other challenges, like, for example, shrinking of farmlands, uh, climate change impacts on agriculture, whether it is limited natural resources or diversion of the food and biomass energy. I would like to mention here diversion, an example that earlier we were growing the crop just to feed the human, but now we are also growing the food to generate the energy. Like earlier we were growing corn to have the corn, but now we are growing the corn to generate the energy as well, like biofuels. Similarly, like energy intensive, so there are some agriculture practices which are highly energy intensive, whether it is fertilizer sources, as you know that Haber-Bosch process, which is used to manufacture the nitrogenous fertilizer like urea and ammonia-based fertilizer. And Haber-Bosch process is considered as one of the highly energy-intensive process which is being practiced or for the human being survival. Second is the water. For example, today we grow the crop, lot of crops which require 3-4 times watering, and although earlier we were doing most of the time we are doing plowing of the water, but these days we are using sprinklers or drip irrigations, which basically saved the water at some extent, but we also need like further some varieties which require less water to produce more. And since we started the intense agriculture, it also affected our soil biological health, because the chemical fertilizers or agrochemicals that we have used in last 50-60 years, that basically because of their poor use efficiency, they have affected our soil health, and whether it is soil chemical health or soil biological health. Soil chemical health means the pH of the soil. As we know that the pH of the soil plays very important role to uptake the nutrients from the root by the plants. And soil biological health, it means that the biological organisms like bacteria, fungus, or the associated flora and fauna present in the soil that basically help in mobilizing the nutrients or making the nutrients in its chemical form, which is preferred by the plants to uptake. So if we have the poor biological health or low microbial populations, or that basically help do not mobilize the nutrients in an adequate quantity, so that plant productivity not realized at its biological potential. When I talk about low use efficiency, and that is affecting our soil biological health. If we just take a look on this paper published in Science, which basically drawing a graph and comparing the plant which is legume or non-legume. Legume means those plants which are having nodules in their root, and non-legume means like plants like maize, which do not have the nodules and cannot fix their nutrients like nitrogen. But if we talk about these nutrients, whether it is nitrogen or phosphorus, and I am taking an example of nitrogen, phosphorus, potassium, because these are the nutrients which capture like 75% of the market size of the fertilizer sector. So these, even if we take an example of nitrogen and phosphorus, which basically has less use efficiency, like around 30%. And if we talk about micronutrients, the use efficiency is even less. Like in some cases, it is just less than 5%. Some of the nutrient less than just 1%. So in that case means from nearly from 50% to 90%, we are losing the chemicals. And when we are said that we are losing, then ultimately they are going to our environment. They are impacting the non-target sources, whether it is our drinking waters or freshwater sources, or our oceans where we grow the seafood, or we do agriculture which is aquatic agriculture. to meet the human food demand. But while the unutilized part, while moving to the environment, it also affects our air, our soil and water. As I gave the example related to the water of the eutrophication, like increasing the nitrate and phosphate concentration in the water, which basically reduce the oxygen concentration by having increased algal bloom and bringing the red tides. Similarly, in the air, like when, for example, if we apply urea or nitrogenous based, ammonia based fertilizers, these basically converts ultimately into nitrous oxide, which is one of the greenhouse gas and ultimately causing towards the global warming or climate change impacts. And then we have already discussed about the soil, that, for example, if we are applying more nitrogenous fertilizer, I'm giving just an example of nitrogenous fertilizer, which reach to our groundwater, and it increases the nitrate concentration in the water. If we take the water sample of various parts of our country, particularly we would like to name some of the states, like for example Haryana, like Punjab, like West Bengal, where the amount of fertilizer, or even some part of the Uttar Pradesh as well, where the nitrogen fertilizer uses is more. Like you might have heard about the ratio, that NPK ratio is imbalanced in our, so you can easily find that on which state the NPK ratio is imbalanced. So wherever the NPK ratio is imbalanced, it means that farmers are using more nitrogenous fertilizer. Because of its poor use efficiency, it is leached to the groundwater, in addition to its going to the air and water. So when it goes to the groundwater, it increases the nitrate concentration. And when the nitrate concentration is beyond the level in the drinking water, it causes the blue baby syndrome or the other associated problems. Similarly, in the air, it emits the nitrous oxide, as we discussed, and causing the global warming, because nitrous oxide is one of the greenhouse gas. And then to address these low use efficiency, there are a lot of developments happening to minimize the impact of this unused fertilizer. At the regulation and policy level, the policy is being formed at national and international level as well. Like for example, 4R nutrient stewardship framework. 4R means like right dose, right concentration, right time, and right place. So if apply the nutrients like that way, then it can at least have lesser release to the environment and more utilization efficiency. Then there are some documents, like for example, the UK government, they are discussing that can we really ban the use of urea by the farmers to crack down the air pollution. So you can see that like how people are focusing on developing the policy, or what kind of future policies will come. Maybe these are the documents just to discuss today, but maybe like these implications will come in the future. And then question comes that like whose fault is this, or how we can solve these problems, or who will pay the price of this, whether it is industry, whether it is governments, or whether it is those who are end users for that. So those kind of discussions are ongoing. At the R&D level, there are several developments to address these problems, whether it is slow release fertilizers or reducing that emission into the environment by coating of those fertilizers. Like for example, you might have heard about neem coating urea, neem oil coating urea. So neem oil coating is basically because urea is hydrophilic in nature. When you put urea out, it basically captures the moisture and like release the nitrogen instantly. That is called burst release. Whereas this neem coating providing hydrophobic core, and that hydrophobic core allows the nitrogen to release in some controlled manner, so that the volatilization is little less compared to the uncoated. Similarly, like multi-nutrient mixing, like mixing of micronutrient and macronutrients, so that we can feed the plant with all the essential nutrients required for that. Similarly, like enabling them to dissolve, which is called popularly in short form, it is called WSF, or water soluble fertilizers. These water soluble fertilizers, what they're doing that through the drip irrigations or through foliar applications to meet the immediate demand in the foliage tissues of the plant, so that it can correct the deficiency of nutrient and improve the crop productivity. Similarly, like co-fertigation, these days you might have heard in the documents, whether it is related to the budget or whether it is economic survey, they are talking about natural farming, or we previously were calling like organic farmings. So what we were using, that we were using some biological organisms to replenish their population in the soil and increase the nutrient mobility or nutrient mobilization and improving the use efficiency. And whether it is organism or the extract of that, there are a lot of development of biostimulants. Government of India also developed a new guideline related to biostimulants as well. So biostimulants are basically the extract of plants or other organisms, and these extracts are being used to deliver the nutrients to the plants. Then the also development related to reduction in the size of the material that we are using, and harnessing the properties of nanoscale for the better use efficiency as well as better dispersion in the media, where it is soil or once it is uptake by the plants, then within the plant tissue. Our laboratory is synthesizing nanomaterials from the bottom of fabrication, but also we do have an infrastructure to manufacture the material from top-down approach. As you know, that top-down means like taking the bigger size particles, then grinding through the physical process or mechanical process and bringing down to the nanoscale with controlled properties. And bottom-up means like start with molecular state materials or precursors, and then allowing them to nucleate or do collisional or condensational growth and arresting their growth at the nanoscale size range. Our laboratory has the ability to manufacture nanomaterials with different morphology, different crystal phase, different composition, different surface properties. And these nanomaterials we use for various different applications, including from crop nutrition to crop protection, for sensing, also for pharmaceutical and environmental applications, as I mentioned the scope previously. If we particularly talk about nutrients or plant nutrients, there are several elements from the periodic table is being actively explored for the crop nutrition perspective. If we look on this periodic table, there are some elements I have highlighted with the blue color border. These are the elements being explored highly by the researchers or by the industry as well, to explore that how we can utilize these elements for improving the crop efficiency. You can see that most of these elements, which are blue in color, are basically the plant nutrients, essential micro and macronutrients. But there are some elements, like for example gold, like silver, like titanium dioxide, which are not the plant nutrients as of today, which is not defined as essential plant nutrients as of today, but these elements are being explored because of their ease of manufacturing, their cost-effective manufacturing, economic way of manufacturing, and then also because these are the elements where we can control various properties of nanomaterials, whether it is crystal phase, whether it is size, whether it is shape, like that. And we can do a lot of fundamental study, which we can translate to the other essential macro and micronutrients. For example, the titanium dioxide, where we have worked on as well. So titanium comes in 3 crystal phases. One is amorphous, another is rutile, and one is anatase. So if you use anatase, then it increases the plant photosynthesis. But if you use rutile or amorphous, this increases the reactive oxygen species in the plant cell. So one can help in increasing the plant biomass, but another crystal form can increase the resistance or have a more crop protection ability. So one is for the crop nutrition, but another is for the crop protection. Similarly, if you have cages structure of nanomaterial, you can take them as a delivery vehicle to deliver the nutrients or active ingredients to the plants. If you have the sphere, you can use the material itself as an active ingredient. So these are the various fundamental applications that we can explore from using the different nanomaterials, which are not even the essential micro and macronutrients. Particularly when we talk about agriculture, it is very important that we can scale up the process. because most of us, when we are researcher at the laboratory scale, we synthesize the material in our laboratory in milligrams, in micrograms, in nanograms, even in picograms, and then we do a lot of fundamental studies. But when we go for application perspective, translation of technology perspective, then we have to think that how we can scale it up. And if we can scale up, then how much its requirement. Like for example, if we make the material which require like 100 kg an acre, then how we will make that, or what kind of cost will be for the end users. So how we can make them cost effective, how we can make them require less, and how can we effectively synthesize in a large or bulk quantity without compromising with their properties. So these are the parameters to think when we develop and translate the product. I would like to show one of the product which are developed by our laboratory, which is Nano Urea. And this product is now with the farmers. Farmers are being used across India, but also the other part of the world as well, even our neighboring countries. And this product is approved by fertilizer control, included in the fertilizer control order of the government of India. Fertilizer control order is basically a kind of a regulatory path where any kind of fertilizers to be sold or sell in India need to be included in that. So this is approved now and being practiced by millions of farmers across the country. And this product has been evaluated as per the Department of Biotechnology guideline and their expertise. Also, it was evaluated by Indian Council of Agriculture Research Institutes, state agricultural universities, as well as Council of Scientific and Industrial Research Institutes. And this product, if we talk about the properties, the Nano Urea having the particle size range of 20 to 50 nanometer. And the key is these particles basically encapsulate the available form of nitrogen, and which can be delivered to the plants in its available form through the encapsulation. And when we deliver to the plants, this releases the active ingredient inside the plant cell. Whereas in the conventional urea, which is generally in the size range of 1 to 3 millimeter or typically 2.8 millimeter, these nutrients typically doing the broadcast application, and when they do the broadcast application, it hydrolyzes on the soil surface or in underground of the water or underground of the soil, and then pick up by the plant roots. And during that process, a major portion, about 50 to 60% of urea get lost, whether it is in form due to volatilization, due to leaching, or due to chemical conversion. And that's what the problem that we are solving through the nano urea. And when we convert the particle size at the nano scale, it helps us to harness the properties of nanomaterial, which is like surface area to volume size ratio, which is much higher than the conventional. Then its physicochemical properties, which we discussed earlier, like quantum properties. Then we have better uptake rate and efficiency at the much lesser volume. And it has better surface area concentration. It has improved the release rate kinetics, that how the nitrogen is released inside the plant cell. And then because of its high surface area to volumes ratio, the bio interaction is also better. So it also stimulates the plant's metabolomics, which basically increase the protein content, increase the gene expression level, increase the RNA content in the cell, or increasing the nucleotide amino acid contents in the cell. If we see the electron microscope image of these nanomaterials, or their hydrodynamic size, or their surface zeta potential. So we characterize these nanomaterials at various parameters, from their shape, their size, their stability in the solvent. And these nanomaterials we test from the fundamental perspective, that if we apply these nanomaterials through soil application, how they will uptake. If we apply through dropcast or through precision foliar spray through using the aerosol, how these particles will get uptake, how these particles get uptake by the plants, and then how they will transport to the different plant part. Because we know that the nitrogen is a mobile element, means that it can transport from older leaves to new leaves. So how that things happen, and how much nanomaterials, for example, because conventional application, we talk about that 120 kg nitrogen in an hectare, for example. But in case of nano, we need to know that how much number of particles we have applied to a plant and what was their concentration. So because when we talk about sustainability and precision, we have to take care of this part as well. And when we have checked the applied of these nanomaterials, we have found that when we apply these nanoparticles through an aerosol applications or dropcast or the soil, then we have found that the maximum absorption we have found in the aerosol application. So what is this aerosol? Is basically a suspended liquid or solid in the air. These particles basically control the droplet size. And when we control the droplet size, then basically it hit the plant, because if the droplet size is bigger, or if it is applied through the soil, which is a like very complex medium, so these particles have an aggregation tendency when they are interact with the soil, or when they any nanomaterials has a tendency to get interact or change their surface property when the medium get changed. So when we precisely apply through foliar application, these nutrients get uptake by the plants very efficiently in its plant available form, and they require very less by mass volume, like a half-liter bottle when we compare to an 45 kg of bag in terms of plant impact on the plants, and they improve the productivity and agriculture sustainability. I was saying that when we mix in the soil, in the previous graph, you have seen that the use efficiency was less in case of the soil, right? So I just would like to mention that why it is so. Because when we apply these material into the soil of different region, different agroclimatic region is having very different properties. Like for example, if we go to the coastal region of Tamil Nadu, or go to the Gangetic region of Uttar Pradesh, or if we go to the desert of Rajasthan, we find the soil property is very different. They have very different salt concentrations, different pH. So when we mix these nanomaterials with the soil, you can see that this SEM image here, that these nanoparticles get aggregated because of different ionic concentrations, different carbon to oxygen ratios, and that basically affect the zeta potential or surface property of the particles. And when these parameters at the surface of this surface of the nanoparticle change, it basically alter the hydrodynamic diameter as well as the attachment efficiency. And when these things are affected, then we get the better impact than the conventional, but we do not get the desired impact. Because when we talk about precision, about the sustainability, then we have to have the nearly 100%, may not be 100%, but nearly 100% potential of that particles. Once we develop these kind of nanomaterials for agricultural application, we test them in the controlled environment, like a vertical farming setup or hydroponic or aeroponic kind of a setup, to see their uptake efficiency, to see their water utilization efficiency, the sunlight absorptions, the reducing the pollution. So various parameters we test from the customer endpoint perspective. And then we test in the real world practice, in the farm field, in the controlled farm field, by that how they are affecting the soil, how they are affecting the plants, the crop productivity, crop nutritional profiles, and so on. And then we test these nanomaterials on various flora and fauna associated with the farm field. And in India, we are having a guideline to evaluate any kind of nanomaterials for agri input and food products in India, that was released in 2020 by Department of Biotechnology, Government of India, with Ministry of Agriculture and Farmers Welfare. And this guideline is talking about basically giving certain tests, certain principles, certain methods to test. And largely it followed the OECD principles, OECD methods or guidelines. And OECD is Organization of Economic Cooperation and Development, which basically developed various guidelines to test the materials from the safety and toxicity perspective. And we have tested this Nano Urea on all the flora and fauna associated with the agriculture, including human cells as well. And we found that this is biocompatible and safe. Once we have ensured that the product is safe for the consumer or the associated flora and fauna, it is performing well in our controlled environment, we test this in all the different agroclimatic conditions, from Jammu and Kashmir to Kanyakumari and from Gujarat to Arunachal Pradesh. Like you can see the digital map where there are certain numbers in yellow, red, and violet color. These are basically the number of trials we have taken during the product was translated from lab to lab. So we have tested at different farm field and we have involved in our trials of more than 11,000 farmers, and we have partnered with more than 20 ICR institutes or state agricultural universities, and we have tested these products for about 3 years on 94 crops and in all the states and central union territories. And what we have found in terms of conclusion, because you know that these are like vast data. So if I say in the conclusion, the average yield increase was by 8%. It was reported by 8%. It reduces the requirement of conventional urea by 50%. Let's say for example, the farmers were using 2 bags of urea. They have reduced at least 1 bag of urea, and they have used the nano urea along with that. And that helped them to increase the yield by 8%. So from the farmer perspective, farmer measured the impact in terms of yield increase, or through their yield, they gain the economy, they get the money. So that's how the end customer look the product. But environmental scientists, environmental or policymakers, they also look at how the transport is easy, the transporting of bag versus transporting of the bottles. The environmental footprints through the transport, environmental footprints by application of nanomaterials, environmental footprints by producing of the materials. Like for example, the conventional urea, if you produce 1 ton, you need 22 gigajoule of energy to produce that. Whereas the nano urea, it requires like just less than 1 gigajoule. So that's how it is being compared from the various footprints or application and implication perspective. This particular product has been approved by FCO and included in the fertilizer control order by publication in the Gazette of India. This is basically a kind of publication through which government informed the public that we have included this product in this fertilizer control order or regulatory order. And then there was an independent evaluation, economic evaluation of our claims. And there was an editorial article in Economic Times by their editors, and it was estimated that in the last financial year, if it wasn't have been implemented, it could have been saved up to 28% reduction in the budgeted fertilizer subsidy, which was estimated at 79,000 crores. This year, nano urea was mentioned or suggested by the Economic Survey of India, which is presented a day before the budget presentation in the parliament. And then it was also mentioned by the Prime Minister. So there were like a lot of questions, concerns, queries, or excitement related to nano urea for in various communities, whether it is farming, related to farming, or related to environment, related to policy making, or the other people who are looking for the economic from the global perspective. So IFCO has developed a dedicated website on nanourea.in, where we have provided all the detailed information that how it was developed, how it is being useful, how it can be used, what are the precautions, safety, etc. So if you have interest and if you have time, then may look on that. This entire presentation was based on some information was taken from these sources, and if you need like more resource to read or review, you can go through that. With that, I would like to summarize that how nanomaterials is helpful for achieving sustainable development goals through precision and sustainable agriculture, and the role of nanotechnology by providing the target delivery of active ingredients, releasing in a controlled manner, keeping them in their plant available form, requiring less by their mass volume, or improving the productivity and the agriculture sustainability, and which can complement the UN's sustainable development goals, whether it is related to pollution, as we discussed about eutrophication and so on, related to food security, that we need to dramatically increase in J-shape curve growth in our food production. Similarly, like biodiversity, because when we provide excess nutrients, that basically that basically degrade the biodiversity, because when there is an excess nutrients and a certain species grow or absorb that nutrients, then the other plants don't grow there. So that's why we have to improve the biodiversity, both at the farm field, both in the forest and farm field, also in the land and water as well. Similarly, like health, because if we produce the biomass, but if the biomass is not nutritious, let's say like these days, when we get any kind of toffee, chocolates, or drink, then we just see that what are the nutritional fact. But what if you go to the farmers market and grab a couple of carrots, and how will you find out that what are the nutrients there? So whether you eat in terms of biomass or eat in terms of nutritional quality, so those kind of concepts are going to come in future. Similarly, like precision in action and outcomes. Action means that how we are producing the material, and outcome means how we are handling once we produce it, whether it is post-harvest technology to save the food waste and something like that. So with that, I would like to thank and acknowledge my R&D team, and also my organizations where I have resources, this thing, whether it is IFCO or Washington University in St. Louis or CRDT of IIT Delhi. And I would like to thank you again, and would like to take your questions. Thank you.
Thank you, Dr. Elia. Thanks a lot for a very interesting lecture. And I'm very sure that my students would have gathered, because just in the last lecture, we were talking about how the form of the nutrient is very important, and plants can take up only few forms, and how the losses are more than what the plants can uptake. And I think they would be very excited to know about this discovery. So thanks a lot. And I open the floor to questions and request the students to unmute themselves and ask the questions.
Hello.
Dr. Elia. Yeah. Yes.
Am I audible?
Yes, please.
Yeah.
Yeah.
So, sir, you talked about Society 5.0 and the preceding societies. So, like unlike other European countries, India looks to have all the 5 kind of societies. We have like all the 5 societies. So, in a way, is it kind of good or bad to have all the 5, so that we can, it's kind of not like that some people are isolated or so, and we can more precisely pinpoint the people and can solve their issue. So is it kind of a good or a very bad situation ki everyone is in different society distinctions, and it kind of violates the equality principle?
Yeah, thank you for the nice question. So I believe that, like in my opinion, these are the transition phase of the development of nation. So the part of the nation is getting more advanced, part of the nation is still in the transition phase. So there is an integration and a transfer or fusion of the technology, or transfer of the technologies from more developed area to the least developed area. Like for example, these days, if we are talking about like more skill development, so there are like a lot of skill development centers are being opened up across the country, so that we can transfer the skills. Previously we were transferring just the like more like an education, but now we are moving towards the skill developments, and that is penetrated even at the village level, even at the tehsil or taluka level, like ITI institutes or polytechnic institutes, like that. Similarly, there are developments related to like increasing the curiosity among the students, or bringing their attention or interest towards the science. We are having like these tinkering labs, Atal Innovation Laboratory or some tinkering labs. These are like some of the examples. Then there are internet connections, which is like governments are trying to connect through the fiber network to all the panchayats, so they can get those things. Similarly, like direct benefit transfer. So these are like some of the examples where India is also moving towards the society 5.0, where the cyber world and physical world is getting connected on developing their skills. So I think like transformation is always good, and adaptation to the new technology is always good, but the pace need to be maintained. The pace need to be fast, because we have to be aligned with the development of technology. Like we should not like develop something today which may be new for the particular area, but may be redundant to the other part of the world. So to get along with the world, we have to increase the rate and pace to be faster.
Yeah. Thank you, sir. I have another question.
Yes.
So you talked about that law and that critical point in the population and the resources. So recently there was a news that the index, I mean, it should be 2.1, the population, what you say that average child or a woman should have, it should be 2.1, but in India it is declining, and it is projected that in 20 years we'll see a decline in population. So would it kind of ease out the problem that we were talking about of the crunch of the resources? So would that ease out the problem, or is it something else? I mean, am I missing something?
No, you are right. See, the rate will grow, but maybe at the slow rate. The population will grow, but at the slow rate. And when we talk about that Malthus theory, the example which I gave from the global perspective, like not only from the localized India perspective, but as a researcher, as a scientist, if we develop like any resource, that resource can be utilized across the world. So when we talk about across the globe, like even today, more than 800 million people don't have the enough food. And there are part of the world where we are wasting like 40% of the food that we are producing today, whether it is in the processing part or whether it is even at the restaurant level. So how best we can use those resources to feed, and certainly the rate of population increase, if that is stable or reduced, certainly that will help to have the better management of the resources in the area where the population growth rate is faster. But when we look from the global perspective, the global population is like right now is around like 7.5 billion is estimated, but the global population going to be around like crossing 9.5 billion by 2050. So we have to see the forecast of our resources, that how can we feed the people in the 2050 from 30 years from now, and which is like not very far.
Yes, sir. Thank you.
Thank you, Dr. Relia. एक क्वेश्चन हमारे ग्रास रूट इनोवेटर से भी है, डॉक्टर रेलिया, तो हिंदी में पूछना चाहेगा बच्चा। हाँ, उत्कर्ष आप पूछ सकते हैं क्वेश्चन।
सर नमस्ते सर, मैं पूछना चाहूंगा कि एक कट्टे के बराबर कितना नैनो यूरिया लगेगा, और उसके साइड इफेक्ट क्या जितने एक कट्टे में आजकल खेतों में हो रहे हैं, क्या वो कम होंगे?
हाँ, अभी जैसे 1 एकड़ के अंदर जो नैनो यूरिया की जो बोतल है वो 500 ml की होती है, आधा लीटर की। तो आधा लीटर की नैनो यूरिया की बोतल को 1 एकड़ में छिड़कना होता है। और अभी जितना यूरिया आप उपयोग में ले रहे हैं, जैसे फॉर एग्जांपल 2 बैग यूज होते हैं जनरली, यदि हम व्हीट क्रॉप की बात करें तो उसके अंदर आप 2 बैग में से 1 बैग को कम कर दीजिए और उसकी जगह पर नैनो यूरिया का प्रयोग कीजिए। तो उससे जो अभी आपका जितना प्रोडक्शन हो रहा है, उसमें एस्टिमेटेड अबाउट 8% आपको उसमें क्रॉप प्रोडक्टिविटी बढ़ावा मिलेगा। और उसके साथ जब आपका पौधा आप हार्वेस्ट कर लेते हैं, उसमें से दाने निकल आते हैं, तो उनका जब आप न्यूट्रिशनल एनालिसिस करवाएंगे, जैसे कि हम गेहूं को हार्वेस्ट किया तो उसके अंदर हम देखते हैं कि गेहूं के दाने में जिंक कितना है, उसके अंदर आयरन कितना है, या फिर उसके अंदर कार्बोहाइड्रेट, फाइबर, प्रोटीन कितना है, तो उनकी मात्रा भी हमें इम्प्रूव मिलेगी कंपेयर टू यूरिया। और जब आप हार्वेस्ट कर लेते हैं तो अपना जो सॉइल है, पौधे की जड़ के नीचे का सॉइल लेके आइए किसी लेबोरेटरी में या कहीं पर घर पे भी, और आप पीएच की स्ट्रिप डाल के देखेंगे तो जो जितना पीएच जहां पर हम यूरिया डालते हैं उसकी तुलना में जो पीएच है वो नैनो यूरिया जहां डाला है वहां पर आपका पीएच बैलेंस मिलेगा, वेरेज जहां पर आपने यूरिया डाला वहां पर स्लाइटली आपको सॉइल ज्यादा एसिडिक मिलेगी, बिकॉज यूरिया अल्टीमेटली इज कॉजिंग द एसिडिटी इन नेचर। देन यदि हम माइक्रोबियल पॉपुलेशन की बात करें सॉइल की, तो माइक्रोबियल पॉपुलेशन भी आपको कार्बन स्टॉक्स ज्यादा होने की वजह से माइक्रोबियल पॉपुलेशन भी इम्प्रूव्ड क्वांटिटी में मिलेगी राइजोस्फीयर के अंदर। Hope I answered.
Thank you. Thank you, doctor. Yes, I think I'm sure that मेरे घर में भी अगली बार नैनो यूरिया का इस्तेमाल होगा इस बार जब गेहूं बोए जाएंगे. Right.
We can take a field trial demonstration there if that is.
Yes, yeah, sure, Dr. Elia, sure. Yeah, so yeah, any other question from our students, our team? Please unmute yourself. Yeah.
Hello, sir.
Yes, hi.
Thank you very much for this time today, because this class was really very in line to our lectures that is going on, where we discuss about the soil, nutrition, uptakes, and nutrients accumulation and all. So really it is very exciting. So sir, I have like many questions, but I don't want to discuss all this here.
You can all can send, if you have questions, you can also send me the question by email, like at rameshralia@ifco.in or rameshralia@gmail.com. You can send me the questions there as well, even after this talk.
So first one is like we are talking about simply the trend is going on about organic farming. And there are also fraud activities going on the behalf of organic farming, because the consumers, they don't have any testing systems like in case of dairy industries. They have test kits that can test the presence of antibiotics, whether the animal was going through some mastitis kind of problems, or even nowadays people are having lactose-free milk. So they have testing systems. So they can spray and then get the result. So can this nanotechnology work on this kind of field? Because all these organic producers are of high commercial values, and people are ready to spend that high value, okay, that money on that particular produce. So how that nanotechnology will be effective in making a test kit that can confirm that yes, this produce, that this vegetable or fruit is from organic farm?
Yes, I think very nice question. I would little bit transforming your question that how can we develop different methods or testing kits to test the quality of the agrochemicals or the materials being given to the farmers, whether it is organic or even inorganic also. So nanotechnology can help us to develop the devices which are like handheld, which are requiring less energy or not heavy to carry. So and we can do like on-site detection of the material quality. Like for example, using, I know some of the laboratories who are working on that. Like for example, in biofertilizer particularly, you talk. So biofertilizer, it is important that what is microbial population in the solution which is given to the farmers. So if the microbial population is at the certain concentration, then only it can work. Then even the microbial population is there, but what is their bio potential? Like for example, some are the bacteria which are like close to degrade or close to die, or the fungus spore which are like close to degrade. So there must be population is adequate, but not in the biological potential which can really transform or act in the field. So there are some people who are using, I know that some people are using graphene and gold nanoparticles to develop the sensor which can detect the microbial population. So these are just glass slide based test. So in the glass slide, you basically use that solution and put a drop of your agriculture input, and that can, based on the color, you can detect that what is their number of the microbial populations. Similarly, people are developing sensors for detect the nitrogen, phosphorus, and potassium and other micronutrient availability in the soil. And then there are I know some people are also developing bio-based solution to detect the pathogenic attack on the plants. So from the organic perspective, it is just limited to like microbial population count and their active potential. But there are developments related to that. And these are like very simple tests. I know like one of the technology which is like near to at the industry translation stage, where they're just using the glass slide, and you just take a drop of that and you can really tell the microbial population. And certainly as a researcher, we have a role to verify and to develop these things.
Sir, that was to explain, this is only for the biofertilizers that we are going to supply to the farmers. My question was, how a consumer like me, I'm going to buy a cabbage which is organically farmed. So how can I ensure myself that whether I am going to pay 100 rupees per kilo instead of 20 rupees per kilo for the normal cabbage, so that this cabbage is organically farmed, or does the supplier is cheating me? How can I confirm this?
Yes. So for that, you need a detection technique which can tell you the residue accumulation. That when so there are certain defined chemicals, like for example, there may be like 500 chemical products or more than that, but there are very limited lists of the active ingredients. So when these active ingredients, whether it is pesticides or whether it is fertilizers, these active ingredients get accumulated in the plant system. So we need to develop the sensor which can basically detect those active ingredients in the plant part which we are purchasing from the supermarket or superstores. There are, for example, there is an chloromethane, which basically one of the very common herbicides or pesticides, or for example, the glyphosates or similar kind of like 2,4-D or DDT. So these kind of chemicals, when they spray on the plants, they get accumulated in the plant tissues. And those detection systems, like there are some detection system already in the market, but now we need to develop like more sensitive. So Nano can help them to lower their detection, like more, making them more sensitive, so that the detection limit can go even at the ppm or ppt level or ppb level, so that even a very small amount of residue can detect at the customer level. I mean, I'm not aware of the product of that kind of product right now, which is available to purchase by the customer, but I know various developments in this direction. There's several laboratories I know that who are working on this.
Thank you, sir.
Yeah,
So
it's a very complex question, Rupesh, I think. Yeah, the question that you have asked is really challenging. And as Dr. Relia said, that there are, organizations which are there to prove that it is organically produced. But actually for a common user, like for the food which is being imported, sent to other countries, exported, those things are in place. But for a common consumer, this is really not very widely available. So I think, as Dr. Relia said, as a scientist, we need to do that, and nanotechnology can play important role. Yeah. Do you have another question,
Yeah,
Rupesh?
I would also like to add for Rupesh that I would like to suggest you one literature on the USDA organic website. You just search on Google USDA organic testing, and there are like several measures they are mentioning that how a common customer can identify the product you are buying is organic or not organic. And there are resources also to how to test. Like in India, we are having EcoCert and BioCert. These are like some of the two companies which I know. There are some others also who do these kind of a certification, like confirmatory test, which can tell you that whether the product is really organic or not organic.
Yes, sir. I noted, sir. Thank you. So just one more question. Like just now, you said that for 1 acre of land, the 500 ml of nano urea is sufficient. Okay. So instead of 2 bags of urea, normal urea, it can be replaced by 500 ml of this nano urea, right? Now the organic.
So I said that we can reduce. Let's say like we are currently using example. If we are using 100 kg of urea, so we can replace at least 50% of that.
Okay. So, sir, recently that the organic farming, farming is all about the output driven, and the farmers are usually they're adding like overdosing of nutrients, urea, just to get more output. Okay, and if it is a nano fertilizer, then the chances of bioaccumulation of those particles, which is going to, like you said, to titanium dioxide. So this is increasing the biomass production of the plant. Okay. And titanium dioxide is also classed like group 2B carcinogen, that is declared by the some IACR or some other organizations. So how to pass this kind of technical information to the consumers, mainly the farmers, that not to overdose this kind of fertilizers, which may lead to like health threat to the consumers.
Yeah. So when we, like as an industry R&D person, I can tell you that when we determine the doses, we keep the doses maybe 10 times lower than its toxicity, or even in some case 100 times of its toxicity. Like for example, this Nano Urea, we test its range of toxicity in terms of LD50, which is called lethal dose at 50% cells can be killed. So first thing, we keep that dose limited. Second thing, whatever the chemicals or product is being translated to the farmers to use, we provide clear instructions on the bottle as a part of the label, which is also a regulatory requirement. But because since the nano is new, we are also providing like dedicated toll-free line for the customers to understand that. We are also doing a lot of in-person trainings, a lot of online trainings, and then we are having vast network of field officers across India, almost in every district of India, to reach out for the farmers for the training and so on. And before that, it is in transition phase development. Like first we develop in the laboratory, we test at our laboratory, then we bring the farmers, some farmers for the training, then we do the farmers scale demonstration, where the related farmers of that village comes. Like for example, you might have seen that more than 11,000 farmers will be tested across India. Then we do test at Krishi Vigyan Kendra, or with State Agriculture University or ICR, or with agriculture officers, involving the agriculture officers, who are basically a person who is responsible to communicate and give the training to the farmers, for providing resources to the farmers at the village level or at the taluka level. So that way, when we do this transition phase translation, then we can communicate the technology to the end customer, that how best we use, and we can also, I mean, in case of this Nano Urea, we are also able to tell our customers that why we developed this product, not because of increasing the productivity or reducing the subsidy or something like that, but this product was mainly aimed to develop to increase the soil biological, to improve the soil biological health, or to improve the environmental impacts which is being posed by the conventional urea, because the impacts that we are seeing through the conventional urea, or low use efficiency of conventional urea, that are more harmful than what we are getting like other impacts. So the product scientifically developed from that perspective, economic benefits for the particular country like ours, and the crop productivity is an additional advantage of this product, I would say. Like from the science perspective, I would say additional, but for the farmers, that are the primary advantage, of course.
Rupesh, I think we can, Dr. Relia, can we take one or two more questions if you have time?
Yes.
Okay, so we can allow
Hello,
others to ask. Yeah.
Hello, sir. I am Vivek Dalvi. I am a PhD student of Professor Anushimali. Sir, I have a question related to Nano Urea product. So this product can, sir, completely replenish the conventional urea usage, where at currently you are saying that it can replace at least 50% of conventional urea back. And also, I would like to understand that is the Nano Urea product is completely of nano nitrogen, or is it also a composite of some essential micro elements also, which are required for the like better plant growth and nutritional value improvement? So that was my question.
Yeah.
Yeah.
Yeah. Go ahead. Finish your question.
Yeah. So, and another question was like when, as Rupesh was saying, that regarding the organic fertilizers. So I always have a doubt in that sense, when we say the completely organic fertilizers, or the organic certifications of the fertilizer products. So as like micro elements are essential to improve the quality of the plants or the leafy vegetables. So in that sense, like how is it really possible that using completely organic product we get the very nutritional plant yield, right, for the consumers? Yeah. So these are two questions.
Yep. So the first part, that can we really replace the 100%? Yeah, we can replace the 100% as well. In that cases, the doses will be different. Since you know that the IFCO is in the urea business also, which conventional urea producer also in the country, and which is one of the largest fertilizer manufacturing and marketing company in India. So we, like, if we say suddenly that okay, replace 100% urea with this new product, then it is very difficult to get the fusion of the technology or translation of the technology. So those are the challenges there. So we start with a gradual reduction and also see their long-term impact. You know, like we in the maybe at the laboratory level or at the research level, we may have the data of 5 to 10 years, but at the farmers field level, at the customer response level, to take those strategic decisions, we have to go like in a gradual manner. So that's why like we are going at the 50% replacement right now. The second thing, that 100% can be replaced. One of the paper is currently under review with Environmental Science Nano, which like we are going to tell the people that like how this can be 100% replaced at what dosage concentration. The second part related to organic and inorganic. See, any nutrients which we are provide to the plant take in an ionic form. Whether you provide zinc sulfate from the zinc sulfate heptahydrate, plant will take zinc ion, or you provide the zinc extract from the algae, let's say which is in the biostimulants, or from any biological sources like zinc mobilizing microorganisms. So they also basically convert any unavailable or complex form of zinc into available form of the source. So the only the reaction medium or the path to convert that zinc ion, that source can be whether it is plant or bacteria or the inorganic chemical compound. Based on that, we define that whether the product is organic or inorganic. Technically, plant take zinc in zinc ion, whether it is coming from plant source, whether it is coming from other biological sources, or it is from the inorganic element salts. So the zinc is zinc, whether it is coming from independent to any source.
Okay. Yeah. Okay. Thank you.
Okay, do we have any other query? Lahu, do you want to ask something? You are working
Yes,
in your
ma'am.
PhD. Yeah, please go ahead.
Hello, sir.
Hey.
Am I audible? Hello, sir.
Yes, please go ahead.
Sir, actually, I have listening this nano area, this nano urea compound for thing since it got launched basically, and I'm following it constantly. And I'm a researcher here in the same department. And basically, I started my research reading your first paper review in SES about precision agriculture. So started my journey by reading your first paper. But sir, actually about nano urea, I'm not able to understand at molecular level what is it, because it is called as nano liquid urea. And something what I have studied by now, that nano liquid systems are very underdeveloped and they are not into some agriculture field. So sir, I cannot understand whether it is nanoparticles are suspended into some solvent or the liquid as a whole is nano. This is the problem.
Yeah, that's really nice question. So these are the nanoparticles suspended in the water.
Okay, sir. Okay. Oh, and those nanoparticles are in nanosine.
No. These are the you are talking about nano urea, right? Because we are also having nano zinc and nano copper, but that is not yet given an approval or included in the fertilizer control order. That application is still under review with the government of India.
Okay. So basically, nano liquid, the nano urea as in liquid that we are listening about is basically a suspension system or emulsion system.
Yeah, these are the basically nanoparticles suspended in the liquid media.
Okay.
Actually, we gave when we were applying the application, we applied with the name of nano nitrogen, but when the government gave the approval, because of some trade name issue and all, it was given the name as nano urea liquid.
Okay. And so one more question, since this technology and this advent of nanotechnology in agriculture is quite new as compared to the other fields, because in other fields there is a very high rate growth. So sir, although this product got approved by the various agencies, as you told here in the lecture, it is already in the use at farmer school, but there is still some level of cynicism about nanotechnology. Because my ma'am itself has taught us in a lecture that there is another concern called emerging nanopollutants.
Yeah.
and how the nanomaterial actually interacts with the whole ecological, biological components.
Yes.
So I have seen papers which I think it is not very clear that cynicism is not gone even in the scientific fraternity.
Yeah. So see, when we talk about nanomaterials application and its implication.
Yes,
So
sir.
implication always comes with the various factors. Like for example, if we talk about nanoparticle toxicity, so factors responsible for nanoparticle toxicity, it starts with the concentration, then starts with the nanoscale properties, and then it starts with the organisms, and then rate and time of applications. So the toxicity depends on these factors. Then if we, like for example, if I take an example of just tea, if we take the tea at certain temperature, then it is non-toxic, or at certain rate of sipping of the tea, the way we sip, right? But if we drink the hot tea, that is also toxic. Even we drink excess water, that is also toxic to the human. So that way, like anything become toxic if it crosses the limit of LD50. That is in toxicological terms, that is LD50, the lethal dose at 50% concentration. The rate, the infusion of nanomaterials, translation of these technologies at slower pace. There are like some factors because of its development, its prices, the customer segment. Because you know that like in agriculture, if you produce a material which is $1,000 cost a liter, nobody will take it. Like if you go to the Sigma Eldritch and see the nano gold particle, or like 1 ml cost maybe like $100. So the farmers won't get it. Like here, for example, we are providing this nanoparticle suspension in just $3 to the Indian farmers, in case, for example. But like there is no other things, and all the particles are consistent of 30 to 50 nanometer. Their morphology is similar, their stability is very well. So like when we produce any material for farmers perspective, we have to produce economical as well. Yes, so that is one of the reason in also cited in many literature also for policy related document, that why these technologies are at the slower pace of the transfusion in the farmers level. Second thing, that why it is so fast in other segment. Let's say like I'm just giving an example of the if a mobile cell phone. Yes, if the cell phone is costly to 1.5 lakh or 2 lakh, people are still line up and purchase it. Yes, and you can get the price, and you don't ask for the segment or outcome or profitability out of that, or what kind of things you will get out of that, right? But in case of farmers, even if you charge 200 rupees, you have to explain the farmers the economic outcome, economic impact. Yes, because the preference is different. For example, farmers, the preference is outcome in terms of productivity and yield. In the other technology, we don't care about the money, we care about the security. Like for example, if my phone has more secure feature, then we are ready to pay more. Yes, in case of medicine, if that thing can save my life, I can pay, like if it is even 100 rupees material but charging $1,000, I can pay that. Yes, sir. Yes, sir. But in case of farmers, like whether it is farmers of US or farmers of India or Africa, farmers are farmers, and it is a very sensitive community, which is like economically marginal. So in farmers related product, we also have to take care of that economic part.
Yes, yes. And so one small, very supplementary question.
Yes.
So as you told me that this is basically a nano emulsion system, a nano suspension system, nano liquid area. So whether you have synthesized the urea by some separate method, or the conventional urea synthesized in the industries you have used it?
So we have developed both the process, so we can start from the raw material, like start from nitrogen or natural gas and start from there. And the second thing, that we can also use the processed technical grade nano urea as a precursor salt to start with our material.
Okay, okay. Because it's a nano synthesis of urea molecule itself, I think, field of research.
Yes, absolutely.
Yes. Okay, sir. Thank you so much. Thank you so much.
If anyone has the question, can also send an email to me at rameshrale@gmail.com or rameshrale@ifco.in. I think I've taken more time now.
Thank you so much, Dr. Relia. I think your time is important, and we have actually exceeded our time that you allotted to us. So thank you very much for this wonderful lecture. Thanks a lot.
Thank you, ma'am, to you too.
Thank you,
Yeah.
ma'am, and thank you all. Much appreciated.
Okay. Bye bye. Good day.
Okay, ma'am. Bye.